Hello everybody, and welcome back to today's grade 12 torque unit topic, hanging signs. Now to understand a hanging sign and how to solve a hanging sign type question, let's first understand the components of the structure. So we have a pole, a beam, which is attached to the pole via a hinge right here, a mast or a sign, and a cable or a rope. Now in grade 12 we have to make a couple assumptions about this system. First of all, the entire system itself is in static equilibrium, meaning that none of the components are in motion. Secondly, the beam and the mass are both uniform. Now, let's understand some of the forces that are acting upon the system. First, we have the force due to gravity of the beam. Now, like I said earlier, the beam is uniform, therefore the force will be acting directly in the middle of it. Second, we have the force due to gravity of the mass or the sign, which will be acting at the attachment point due to the fact that it is uniform. Third, we have the tension force, and like I said earlier, it will be acting in the opposite direction of the force due to gravity of the beam and the force due to gravity of the sign or mass because we are in static equilibrium, and this force is at an angle, we call it theta. Again, because we are in static equilibrium, this beam cannot be pushing through the pole. Therefore, we have the force of the hinge that will be acting in the opposite direction at an angle that we'll call phi. But you know what? This is a kind of boring way to learn, so why don't we just go and make it? To find the measured values for this problem, I first weighed myself on the scale and converted it into kilograms, and then following that I weighed myself with the beam on the scale, subtracted my weight from that total value, and then converted it into kilograms to get the mass of the beam. Now here is a question that perfectly resembles this system that I've created. It seems Throckmorton has gotten himself into quite the pickle. Throckmorton, who has a mass of 70.31 kilograms, is hanging on the edge of a 0.96 meter uniform beam which has a mass of 3.18 kilograms, which is being upheld by a rope that is attached to a pole at a 30-degree angle. Part A. What is the tension force on the rope? And part B, what is the force and the angle of the hinge force? This type of hanging sign question is a textbook example of the type of question you'd get in a grade 12 physics class. And now, here's how to solve it. Alright, so here we are. Now, like any physics question, let's start with writing down our knowns. So first we have the mass of the board or beam is going to be equal to 3.18 kilograms. Now we have the mass of the sign, or in this case Throckmorton, and that is going to be equal to 70.31 kilograms. Length of the board is equal to 0.96 meters, which means the R value of the board is equal to 0.48 meters. The R value for the sign is equal to 0.96 meters. The R value of the tension, which would be on the rope, is equal to 0.96 meters. And theta is 30 degrees. Now we are looking for tension force, so that is equal to question mark. And the force of the hinge, that is also equal to question mark. And then the angle of the force of the hinge, which we do not know either, so we'll represent it as a question mark. Now, the one assumption we have to make is that gravity is equal to 9.81 meters per second squared. Now on to the free body diagram. So we're going to have a post, a beam, a sign hanging off of that beam, and then in this case we had a rope stretching all the way down to the end of the beam there. The angle is theta. You have the force of the tension, force due to gravity of the sign, the force due to gravity of the board or the beam, and then we have our force of the hinge, which is acting at an angle of phi, which we do not yet know. So in part A of the question, we are looking for the tension force. Now to find that, we're going to use the sum of the torques, but first we have to understand what torque is. And as we know, the definition of torque is torque equals force times R times sine theta. And just a key thing to remember that Fg is equal to mg. All right, now let's start with the sum of the torques. And of course, since we are in rotational and static equilibrium, the sum of the torques is equal to 0. Now let's write out all the torques that we have acting on our system here. Torque of the hinge plus torque of the tension minus torque of the board minus torque of the sign is equal to 0. And out of these, you have to pick one. We have to pick a pivot point, and I say the pivot point we should choose will be right here on the force of the hinge, because this part here we know the littlest about. In fact, we know no information about it, just that it has a force and it has an angle. So we'll take that the pivot point, which means our value would be 0, so that will go to 0. Now we have the torque of the tension is equal to torque of the board plus torque of the sign. Now we can break that down into its components. So we have the force of tension, R value of T, sine of 30, or theta, in this case, is equal to the mass of the beam times gravity times the R value of the beam times sine of 90 degrees plus mass of the sine times gravity times the R value of the sine times sine of 90. Now, it is a sine of 90 since all the forces due to gravity are acting at a perpendicular angle to the beam here. So they're 90 degrees, which will mean that they will reduce to 1. Now to isolate the tension force here, we're going to divide by the R value of T and then sine of theta. So this will reduce to 1. And then divide this on the other side, RT sine of theta. So we have our finished expression here for the tension force, which is MBGRB plus MSGRS, and that is over RT sine of theta. So now let's write that in with our values. So tension force is equal to 3.18 kgs times 9.81 meters/second squared times 0.48 meters plus 70.31 kg multiplied by 9.81 meters/second squared multiplied by 0.96 meters, and that will all be divided by 0.96 meters times the sine of 30 degrees. And again, I'll put a bigger set of brackets around that so we know that the operation is happening after. And the meters will cancel with meters, leaving us with newtons, or kilogram per meter second squared. And then our final force of tension is going to be equal to 1,410.68 newtons. Alright, so after we found the tension force, we can now solve part B of the question, which is finding the force of the hinge and the angle that it acts upon. So for B, let's start with the sum of the forces in the X to give us one component of the force of the hinge. So sum of the forces in the X direction, and as we know, we are in static equilibrium, so it is going to equal 0. So as we look at it, we have two. So we have FHX, which will be acting here, and FTX, which will be acting here opposite to each other. So FHX minus FTX is equal to 0. FHX is equal to FTX. FHX is equal to the force of tension times the sine, or rather the cos of theta. Now this means that FHX is equal to 1,410.68 newtons multiplied by the cosine of 30 degrees. And this will give us a value of 1,221.68 newtons. Now let's do the summation of the forces in the y direction. And again, static equilibrium will be equaling 0. So force of the hinge in the y direction plus force of the tension in the y direction minus force due to gravity of the beam minus force due to gravity of the sign is equal to 0. Force of the hinge in the y direction is going to be equal to FGB plus FGS minus FTY. Now let's write our values in. FHY is going to be equal to, now remember FG equals mg, so you're going to have 3.18 kilograms multiplied by 9.81 meters per second squared plus 70.31 kilograms multiplied by 9.81 meters per second squared. And again, that will be subtracted by 1,410.68 newtons. And this time, instead of cosine, we have sine of 30 degrees. Now this will equal out to 15.60 newtons. Now to find FH, or the force of the hinge by itself, we're going to use Pythagoras' theorem, which tells us that a squared plus b squared equals c squared, and like we said, we're finding the hypotenuse here. So FH is going to be equal to the square root of FHX squared plus FHY squared. So FH is going to be equal to 1221.68 newtons squared plus 15.60 newtons squared, and all of that square root. So FH is going to be equal to 1,221.78 newtons. Now to find the degrees that this will be acting on, let's look at phi. So we know these two values here, FHX and FHY. We know that phi will be equal to tan, or inverse tan rather. So if we divide the opposite by the adjacent side, we will get the angle. So tan of -1, and then opposite, which in this case is the y direction. So we have 15.60 newtons divided by 1,221.68 newtons, and that to the 10 to the -1 is going to be equal to 0.73 degrees. Now let's look at this again. Force on the hinge is going to be equal to 1,221.78 newtons, and we're going to put the at symbol, 0.73 degrees, and if we're looking at this from a torque standpoint, we can say that it is acting in the counterclockwise direction. So this is how you solve a hanging sign question. Thanks very much and have a great day.